Have you ever seen a student who studies for a test by memorizing every single question and answer from past exams, only to struggle when faced with new, slightly different questions? This common scenario perfectly illustrates a core challenge in deep learning called overfitting. It is a critical concept to grasp for anyone working with artificial intelligence and machine learning models. Overfitting occurs in deep learning when a model learns the training data too well, capturing not just the underlying patterns but also the noise and random fluctuations specific to that particular dataset. Essentially, the model becomes overly complex and memorizes the training examples, losing its ability to generalize effectively to new, unseen data. This leads to excellent performance on the training set but poor performance on any real-world data it encounters later. The primary reason for this behavior lies in the model's capacity relative to the complexity and size of the training data. Deep learning models, especially large neural networks, have a vast number of parameters, sometimes millions or even billions. This high capacity allows them to fit extremely intricate functions. However, if the training dataset is small, noisy, or lacks diversity, the model exploits its high capacity to learn spurious correlations instead of the true, robust relationships. Think of it as a model trying to find meaning in every single data point, even if that data point is just an outlier or a measurement error. To counteract overfitting, practitioners employ various strategies. One fundamental approach is to increase the amount and diversity of training data, as more data makes it harder for a model to simply memorize patterns. Another common technique is regularization, which adds a penalty to the model's loss function based on the complexity of its learned parameters. Methods like L2 regularization, also known as weight decay, actively shrink the weights of the network, discouraging overly complex models and promoting smoother decision boundaries. This encourages the model to relying on multiple features rather than becoming overly dependent on a few. An insightful concept related to overfitting is the bias-variance trade-off. A simple model with high bias might underfit, meaning it is too simplistic to capture the true underlying patterns. Conversely, an overly complex model with low bias can easily overfit, showing high variance in its predictions on new data. The goal is to find a sweet spot where the model is complex enough to learn the true relationships but not so complex that it starts memorizing noise. Techniques like dropout, which randomly omits neurons during training, also provide an effective form of regularization by preventing co-adaptation of feature detectors. Understanding why overfitting happens is more than just academic knowledge. It empowers you to build more reliable and robust deep learning models. By recognizing the delicate balance between model capacity and data quality, and by actively applying regularization techniques, you ensure your models can truly learn generalizable insights from your data, making them valuable tools for real-world applications and avoiding models that merely parrot their training examples.